Hi, we're going to finish up focus one, talk about real gases and a little bit about the kinetic theory of gases. Okay, so topic 1B on the kinetic model of gases. You've learned a little bit about that back in Chem 107 when you learned about the ideal gas law and then real gases. So we're going to learn this in the context of a lab that one group will do. So I'm not going to go over it right now. The only thing you'll need as you're reading is this equation number 17b on page 16. Then that will help you understand how you can liquefy a gas into a liquid if you can't find a substance that's below its vaporization temperature. So that equation, and you only need it conceptually. So we will move into the next topic then. And we're just going to talk about real gases, which you've already been introduced to too, but you'll see it in a little bit different context here. So the key idea is that you have attractions and repulsions between gas molecules, and they account for modifications to the isotherms of a gas and account for critical behavior. So that accounts for the fact that we don't get those beautiful parabolas when we plot pressure versus volume when we measure it. And it also accounts for the fact that you can't always compress a gas into a liquid if you're above a critical pressure or above a critical temperature. So we'll talk about those properties which you've been introduced before, but you may have forgotten them. So in terms of the quantities introduced, a perfect gas is one for which the mean free path of the molecules in the sample is much greater than the diameter of the molecules. The mean free path is just how far a molecule travels before it collides with another one. That was from the kinetic theory of gases. And so really all it's saying is a perfect gas is one that really doesn't collide with other molecules because it's not at a very high pressure and not at a very low temperature. So there are other ways of saying that. You could say that the particles don't interact with each other and they don't occupy any of the volume, which is the same thing as they don't repel each other. So using the mean free path isn't necessarily the only way to talk about a perfect gas. So we're talking about systems where you only have kinetic energy when we're talking about perfect gases. This little chemist toolkit is really important to read because we're going to do a lot of derivatives in thermodynamics. So you have to remember what a derivative is. It tells you the slope. The second derivative tells you the curvature, whether it's curving up or down. And this toolkit has a little bit on how to take derivatives, and you can remember that in derivatives. I remember how to take most derivatives. I don't remember how to take very many integrals, but you can also use Mathematica. So the molecular interactions that we're talking about, so if molecules are fairly far apart and they get closer together, there's often an attraction. So this shows that as they get closer together, there's an attractive force that would be probably creating some sort of intermolecular force, like a hydrogen bond, something like that as they get closer. But then as you try to force them closer together, essentially you're trying to force their nuclei to interact, and that's going to be repulsive. So depending on where you're at, you could have molecules in the gas phase having attractive forces or repulsive forces, and those are going to change the behaviors in different ways. So the critical temperature is the point on a curve that resembles a perfect gas isotherm, which indicates carbon dioxide is a gas at that point. So, oops, we are to be looking at this. Oh, I'm sorry. So this is just a blow up of figure 2. So the important thing is if we have this gas here, and we start at A, we start at A. Nope. Go down here. Start at A. Sorry, I was on the right line. So we start at A, and we start to apply pressure. And when we do that, the volume is going to decrease. And this is going to look similar to an isotherm for a perfect gas. Same thing as you go from B to C. But then you have this super strange behavior. When you get to C, all of a sudden the volume goes down, but the pressure stays the same all the way until you get to E. And then all of a sudden, as the volume decreases just a little bit, the pressure goes up a lot. So it takes a lot of pressure to change the volume a little bit. So what's going on here is you have a gas, but you're below the critical point. So you're below the point at which it can be compressed to a liquid. So going from C to E, you're decreasing the volume because the molecules are interacting and becoming a liquid. Then once it's all a liquid, it's going to take a lot of pressure to make the volume any smaller. So that's this discussion right below your figure 2, which this is just a little bit larger. So the step from C to E corresponds to the molecules being so close together they attract each other and cohere into a liquid. Then the step from E to F, that's where they start to, you have a liquid, and compressing a liquid any further is actually forcing the nuclei close together. So that's not going to happen. So there is one isotherm on here where this one right here at 31.04, where I've colored it in a little bit with yellow. It's the isotherm where above this temperature, you don't go through that gas to liquid phase or vapor to liquid phase. And what you actually have, we'll see in a second, is defined as a gas. So there's no pressure you could apply when you're above this temperature of 31.04 to make it into a liquid. So that will be, when you're at that point, you have the critical pressure, the critical volume, and the critical temperature on that graph. So by definition, a vapor is a gaseous phase of a substance below its critical temperature. So that would be like you have a sample of water and there's gas above it, gaseous water. That's really best described as a vapor because it could be condensed to a liquid. But when you're above the critical temperature, you truly have a gas. You can't liquefy even by compressing it. So this little paragraph here just talks a little bit about supercritical fluids. So fluids, when you're above that temperature at which you can compress them from a gas or from a vapor to a liquid. And when you're up there, you actually call it a fluid when you're above that temperature, often because its density is so high. So oftentimes this compression factor is used as a measure of how perfect a gas is. So the compression factor Z is the volume, the molar volume that you measure compared to the perfect gas molar volume at those conditions of temperature and pressure. So if this was 1, you'd have a perfect gas because the molar volume would be what you'd predict from a perfect gas. But in general, if you're not in a perfect gas situation, you can replace the molar volume. You can replace the molar volume of the perfect gas with its relationship to RT and P from the ideal gas law. And when you put that in, your Z will be the pressure times the molar volume that you measure divided by RT will be your compression factor. So this graph is just showing you some compression factors, and here it is just blowing up a little bit. So some things, so perfect gas would have a compression factor of 1 no matter what the pressure is. but we know that gases behave more perfectly as the pressure goes down. So what you see here is some substances will actually have a compression factor lower than 1, and some will have compression factors higher than 1. Often what's the most common is this situation where it's lower than 1 until you get to some pressure, and then it's above 1. And so when you think about that, up until this point, the methane is being dominated by attractive forces. So the gas molecules are attracted to each other. That's lowering the molar volume that you would predict if it was a perfect gas and not interacting. But then you get to some pressure at which the particles are so close together because you have so many in there, so such high pressure, that the repulsive interactions start to dominate. So this would be the point it goes from attractive forces dominating to repulsive. Some things like H2, it has such a weak dispersion force that it never has any attractive forces that make the compression factor less than 1. So depending on the substance, you can learn something about the interactions of the molecules, looking at how the what the value of Z is, the compression factor. So let's just look at a problem, self-test. Self-test 1C.1 on page 27. So it asks us, it says a gas is at 350 K, 12 atmospheres, and it has a molar volume 12% larger than that calculated from the perfect gas law. Calculate the compression factor under these conditions and the molar volume of the gas. Which are dominating in the sample, the attractive or the repulsive forces? So what I did was I calculated the molar volume of a perfect gas under the conditions they gave me, and I got 2.7 decimeters cubed, and I'll use that in a second. Or actually, I won't use it. It just asked me to calculate it. But to figure out what the compression factor is, I take what it would be for a perfect gas plus 0.12 times the perfect gas, because it said it's 12% greater. So the perfect gas is going to cancel from each, and I get a compression factor of 1.12. So that should mean that the forces dominant under these conditions should be repulsive, because the volume is bigger, so you're having a harder time getting the molecules to stay close together. Okay, so once you know that your gas isn't behaving ideally, there are different ways to correct for it. So you can take PV equals nRT and add correction terms, which we'll look at in a second with the van der Waals equation of state that you would have seen before. But often it's common to use other things like series expansion, which there's a little toolkit at the end of this section to talk about, to remind you what it means to do a series expansion. But you can say a perfect gas would have Z equals 1. And if it's not perfect, we can make corrections. So we can have a B and C, and we can determine these experimentally. They're called the virial coefficients. So that's one way to make corrections, is to have terms. So each time you go up, the volume is going to be a positive number. So it's going to get smaller and smaller, the correction terms, as you go up, because you're dividing by V squared. And so usually you only need a couple terms. So oftentimes Z just can be approximated as 1 plus B over the molar volume. Depending on where you are and how accurate you want to be, you may use more and more of those correction terms. you can then change this directly into an equation of state. So this is just looking at a measured Z and determining what B and C would be. But then you can sub in for Z what we had earlier. Well, we had earlier this relationship that Z equals P molar volume over RT. So just look back a slide or two. So you can sub that in for Z. And now you have an equation of state. You have a relationship between pressure, volume, temperature, and number of moles, because this is molar volume. So if you take the molar volume and pull N out of that, so you can get regular volume, and then you have the virial equation of state relationship, and you would have gotten the B and C by doing experiments to get a Z and then fitting it mathematically to that function to get B and C. Sorry. I guess I didn't do that self-test. So the second virial coefficient for ammonia is this. Determine the pressure at which the molar volume is this. So that would mean you just plug it into that relationship right here, and you're going to be truncating it as just the first term here, the NB, and solving for what the molar volume is. So go ahead and stop and do that. And just make sure you get the right answer. So doing a series expansion is often mathematically very accurate, but oftentimes it doesn't give you any information about what B and C tell you. So what are those corrections to a perfect gas tell you when you're correcting it that way? So it's often common to find another expression that you can fit your data to that gives you some information about the attractive and repulsive terms. And that's what the van der Waals equation of state does. So the first thing it does is it makes a correction for the repulsive terms, which is also the same thing as saying that if the gas particles repel each other, then your particles can't really be in the entire space of your container. There's some volume that it's excluding because of those nuclei repelling it. So you take the volume within PV equals nRT, and you subtract the number of moles times some B, which is an experimentally determined constant that's a function of what the structure of your molecule is. B is theoretically close to equation 4, but it's better to think of it as an empirical parameter, which you can fit by just measuring pressure, volume, and temperature and fitting it to the van der Waals equation of state. So the first thing you do is add that term. So P equals nRT over V, but now we're going to say P equals nRT over V minus NB. So we're taking into account the fact that the volume isn't all accessible to the gas particles because they repel each other. The second term that we're going to look at is reduction in pressure because of attractive forces. So this is looking at what that term will be, and it'll be A times N over V squared. And the N over V squared is, the first one is reflecting the fact that there's a reduction in frequency of collisions. So if they don't collide as much, there's less interaction. And then the other factor is the reduction in the strength of that impulse. So if the particles are attracting each other, this term can go in and it will alter the pressure. So, or it will represent how the pressure is altered because of the attractive forces. So you end up with this whole thing. So we take the pressure and we subtract from it A times N over V squared. and we subtracted from the volume that term that takes into account the fact that the particles repel each other and can't occupy the same volume. And so if you fit your experimental data to the van der Waals equation of state, you can get some idea about the attractive and repulsive forces in your gas. So it's a different way to represent non-ideal behavior, but it's a more physically intuitive way to do it. So depending on what you're interested in, if you're interested in more exact work, you'll probably use the virial equation because you can keep adding more and more corrections. If you're more interested in seeing how your gas is behaving and what the forces are important, you'd probably use the van der Waals equation of state. This last little section, which you can look through, it's not super important for us, is where you can see that the B from the virial equation can be related to the A and the B from the van der Waals equation. Yeah, this right here. And that's just algebraic manipulation to relate the two equations and then solve for big B in relation to little b and A. So I want you to read through the liquefaction of gases. So if something forms a liquid way below the temperature at which you could make a refrigerator, then you have to find another creative way to liquefy it. And often how you do that is by allowing a gas to expand through a hole. So because as it expands through the hole, if there were attractive forces holding the particles together, as they move apart, they're going to slow down. So this section is gives the analogy of you throw a ball up and it slows down because it's going against gravitation. And so same thing here. So as they slow down, what you saw in that one equation I told you to notice in section B was that the mean velocity is proportional to t to the 1/2. So that means as the particles slow down, the temperature has to go down in order for this to be true. So read through that section, and it's interesting. That'll give you some insight into how we make liquid nitrogen and other liquid gases that their temperature when they're liquids is way below the temperature you could make a refrigerator. So that's our introduction to gases. Now we're going to move into thermodynamics. And the whole goal in our thermodynamic study is to understand why reactions go in a certain direction and when do they reach equilibrium. So we're going to go through the first, second, well actually the 0th, first, second, and third laws of thermodynamics. And we're going to see that really the second law, the law that says the entropy of the universe is increasing, is the important one. So that will be our next chapter, which I really enjoy. So see you there.